Okay, let's start. In the last lecture, we have learned what is echelon form and what is the reduced echelon form. Here, as you can see here, this is the general form of echelon form of matrix, and as you can see here, this is the general version of the reduced echelon form. And we also learn what is the pivot position and what is the pivot and what is the pivot column. Yeah, pivot position, right? So from now on, we will learn what is the low reduction algorithm. So actually, these low reduction algorithms, we already learned how to solve this linear system. But by using the low reduction algorithm, we will formulate what we have done so far is as the systemical way, right? So this is called the low reduction algorithm, or called the Gauss elimination. Actually, it is not exactly same as the Gauss elimination, but we could say it is similar to the Gauss elimination method. Okay, so in this lecture, we will call these algorithms as a low reduction algorithm. Okay, here is the example. Apply the elementary law operation to transform the following matrix is into the echelon form and then into reduced echelon form. Okay, let's remember. Okay, I let you know in here why we should learn the echelon form and reduced echelon form, because we have this matrix A, and we want to find the solution of this linear system. But in the original matrix, it is really hard to find the solution. So what we want to do is to convert this matrix into the relief matrix. So to make this original matrix in a relief form, we want to apply the sequence of elementary law operation step by step. So the intermediate matrix is called the EF echelon form, and then we finally get the reduced echelon form. What is mean? If we find the reduced echelon form for the arbitrary matrix, then we can say that we have a solution of this reduced echelon form, and this solution set will be the solution set of the original matrix. Okay, so that's what we want to do. Yeah, here. Okay, so actually, this is just the low reduction algorithm. So first of all, let's say this is our matrix. Okay, so let's say this is augmented matrix. Okay, so this matrix consists of the 3 rows, right? And what? 6 columns, right? How many equations in this system? I asked you several times, right? How many equations do we have? 3 equations, right? Because we have 3 rows. Then how many variables we have? 5, right? Because this is augmented matrix. Okay, so we have a matrix something like this. So what I want to do first, make this original matrix in a echelon form. Okay. The step 1. Let's say step 1. Step 1 is to begin with the leftmost non-zero column. In this case here, this is leftmost non-zero column, right? Let's say this is the pivot column, and pivot position is at the top. What I mean? What I mean is, because we want to make the pivot position, first pivot position here, right? And then if we make this position as a pivot position, then we can do the similar procedure on the following remaining matrix. Okay, so we want to make this position as a pivot position, but as you can see here, this is the 0, right? So it's not a. So if you remember the what is the pivot position, it should be non-zero values, right? So but in this case it's a 0 value. Then how can we do that? How can we solve this problem? Okay. This is second step. So in the second step, we want to select the non-zero entry in the pivot column as a pivot, right? But in this case, it's not a non-zero value. So if necessary, interchange the row to move this entry into the pivot position. So do you remember what is the interchange row? Is the second operation in our elementary, element row operation, right? There was a 3 kinds of operation, right? I believe you can remember what was the elementary law operation. Okay, so anyway, so if there is zero values in the pivot position, we should interchange the law. Okay, so let's go back to the original matrix. Okay, there is 2 possibility. The first one is the row 2, second one is the row 3. We can use any kind of row as alternative of the row 1. Okay, but there is a very how to say, interesting concept called partial pivoting. What does that mean? Actually, there is a 2 possibility for next row 1, but anyway, we have to choose the which row is better, right? Anyway, we can solve this linear system using any rows like the 2, 1, 2, R2, R3, right? But in the computer, they used some kind of the how to say method to solve this linear system. Let's say they use the row reduction algorithm. They have some in the computer. They represent these values as a what? some kind of the binary bit value, something like this. So let's say if the computer used the 4-bit like this, so we can represent these three using only using this binary 4-bit, right? So, but in this case, the 3 or -7, it's okay because this is just a simple integer value. But what about this, like the 0.3333, something like this, 0.1234, something like this. It is hard to represent this infinity, the very long floating number within a predefined bit representation. So in this case, we need to round off to remove the remaining part. Actually, it is might be hard for you to understand, but just remember. So, okay, in this case, what it means, we need the number that is much easier to represent within our computer formatting, right? So what does that mean? So okay, let's think about more easier case. Okay, let's say there is the 1.3 0.00311 case. Okay. Oh, something like this. 0, 2, 3, something like this. Yes. Yeah, let's see this example. Okay. So if we want to make this position as a pivot position, we have to interchange the row 1 with row 2 or row 3, right? So if we exchange the row 1 with the row 2, the matrix looks like 1, 1, 1, 0, 2, 3, 0.3, something like this. If we exchange the R1 to the R3, the matrix looks like what is that? Yeah, second row remains unchanged, and 0, 2, 3, right? So after solving the method using some kind of the procedure, then when we want to find the solution of x1 here, let's use another x1 here. So let's say this is a case 1, this is case 2. In case 1, 1 times x1 blah 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 equal blah blah blah, right? So in this case, x1 equal blah 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 over 1, right? But in the case 2, 0.003 times x1 blah 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 equal blah 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 blah. In this, x1 should be 0.003 blah blah blah. Okay, so let's think about that. So because these numbers, because if you remember this part, if there is round of error, right? let's say there was a round of error here and here. Then if we divide this round of error by 1, round of error is just remain, right? But if we divide this round of error by using this value, it will be it will be larger than the original round of error, right? So it means that so if when we exchange this row 1 with the other rows like R2 or R3, we should choose the biggest absolute value in this column. Okay, in this case it should be 1 because 1 is larger than this value, right? So this is called the partial pivoting concept. Okay, so fortunately in this case these three values is equal to this value. So in this case we can use the any rows like row 2 or row 3, but if this value is equal to 2, I would say selecting this row is better than selecting this row. Okay, so this is the partial pivoting concept. Okay, anyway, let's go back to our problem. Okay, in this case, we want to change the R1 with R3. Okay, so okay. Oh, sorry about that. Okay, so this is R1 and R3. We want to exchange those rows, so we will get this matrix. Okay, so this is the step 2. Okay, so there was step 1 and step 2, and what will be next? Then in step 3 we want to use the row replacement operation to create the zeros in the whole position below the pivot. What does that mean? Okay, let's see here. Okay, we choose this position as a pivot position, right? So what was the conditions of the echelon form? The below values of the pivot position should be what? 0, right? Should be 0. Then how can we do that? We can use these values to eliminate these values. In other words, we can use this row to eliminate this value, right? So how can we do that? We can just multiply this row by -1 and just add with original row 2. Okay, so yeah, use this one. Okay, so what does that mean? So the first row remains unchanged, but what you want to do original R2 minus R1. Okay, so in this case 3 -3, let's say this is R2, 3 minus 3 minus 7 plus 9, 8 minus 12 minus 5 minus 9 plus 9, 8 minus 6, 9 minus 50. Okay, so this is the new row 2. Okay, I highly recommend to do this yourself. Okay, anyway, we can get a new row like this. Okay, so this is a new pivot column, and this is the pivot position. Okay, so and there is zeros here. Okay, so we could say, okay, we remain the just one variable, this one first column, right? Then what do we do next? Okay, so because we already deal with this column 1, so we should think about another column. Let's say column 2 or column 3. Okay, so in the step 3, cover or ignore the row containing the pivot position and apply step 1 to 3 to the sum matrix that remains. What does that mean? Okay, we deal with this column already, right? That in this case we don't need to consider this row anymore. Our main considerations is here. What do you want to do next? We want to find the new pivot position here and make these values as a 0. Okay? Why should we do that? Because we want to make this matrix as a echelon form, like something like this, right? So okay, so for this new sum matrix, we will apply the step 1 through the step 3 on this sum matrix. After that, we will also apply the step 1 through the step 3 to the another sum matrix, something like this, something like this, something like this. So this is the kind of the iterative solution. Okay. So in this case, let's just consider this second sub matrix. Okay. So what do we want to do? We want to select this position as a pivot position. Sorry about that. Okay, so how can we remove this part? How can you do that? Let's say this is another row, this is another column, another row 2, row 3, and how can we do that? We can do row 3 minus row 3 minus, how can we do that? 3 over 2 row 2. Okay, so if we do like that, the row 3 will be 3 minus 3 over 2 times 2 and minus 6 minus 3 over 2 minus 4, right? Just collect, right? So 6 minus 3 over 2 times 4 minus 3 over 2 times 2 negative 5 minus 3 over 2 times negative 6. Okay, this will be the new row 3. This all elements are mapping here. Okay, like this. Anyway, after this procedure, we will get the new matrix, something like this. Okay, so we have a pivot position here. We have a another pivot position here. So in this case, this one and this one is the pivot position, pivot column, and this position is the pivot position, right? So okay, then what is the next sum matrix? Like this. What is the next sum matrix? Next sum matrix are here, right? But as you can see here, okay, so in this case, when we cover these two rows, because we already found the pivot positions here, sorry about pivot position, there is only one rows here, right? So, but in this case, to reduce this row, this only one row, we don't need to the step 1 through the step 3, right? So we could say that we reach the echelon form of the full matrix. Okay. So what this mean? Starting from this original matrix, we arrive the here, this echelon form of the matrix. Echelon form of the matrix. Okay, so this is the step 4, right? So this is the step 1 through the step 4. Okay, now we have a echelon form, and now we are gonna make the reduced echelon form from this echelon form. Okay, how can we do that? Before that, we have the 3 pivot positions are here, 3 pivot columns are here, right? Then what is the new reduced echelon form? Can you imagine? What was the reduced echelon form? In the reduced echelon form, the pivot position should have value 1, right? So in this case, 1, 1, 1, 0, 0, 0, 0, 0, something like this. And what was the another constraint? The above entry also should be 0, right? And the right hand side will be some kind of value, blah 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 blah. Okay, so will be the reduced echelon form. Then how can we derive this? REF. How can we derive this? Oh, by the way, actually, these values don't necessary to be the 0, because in the conditions of the reduced echelon form, there was no statement about this position, right? They only deal with the below and above position, right? So this value could be any kind of number. Okay, so this is a reduced echelon form. Then how can we make it? Because we already have the pivot positions here. So by using this law, we can remove these values and this value, right? Right. How can we do that? Because let's say this is R1, R2, and R3. If we just replacement, if we just use the replacement operator like the R2 minus 2 R3, something like that, and then we can remove this part, right? The similar way, if we replace the original R1 by R1 minus 6 times R3, we can remove this part, and then we can make these values as a 0, something like this. Yeah, so we can, by using these kinds of low operations, we can finally arrive at the reduced echelon form. Okay, this is the step 5. In the step 5, we want to create the 0 above each pivot that I mentioned before here, right? Here. If pivot is not 1, make it 1 by scaling operation. Why? Because we want to reduce the echelon form. Okay, so yeah. So this was the R2 and R3. Then if we use this operation, we can get this new matrix. Okay. Okay. So let's write again. R1 minus 6 times R3. Okay. Minus 6 times 6. Okay. And R2 plus minus 2 times R3. Okay, so the result looks like this. You can do that yourself, right? I believe so. Please do it yourself. Okay. Anyway, I already know the solution, so I will start from here. Okay. So we have this matrix. Then what is the next step? We want to reduce this value, right? We want to reduce this value because we want to make this part as a 0, right? To this end, we can just to do something like this. R1 plus 9/2 times R2, right? Then it is gonna make this value as a 0. But we can do that. We can do like that. But before that, we can start make the pivot position as a 1 first, right? Like this, rather than this value. How can you do that? Just divide this row by 2. Okay, then it will be looks like this, next like this, and we have a 2 pivot position with the value 1. Okay, and then yeah, let's say we do like this, right? And then what we do, we want to delete this part. Then we can apply R1 R1 plus 9 times R2 like this. Then you will make some, let's do like that. So 1 plus 9, 12 minus t, right? And minus 9 plus to like this. It will be 0 minus 2 plus, what is that? 63, right? So it should be 0, negative 6, 9, 0, negative 17, 2. Okay, so we eliminate this part here. Okay, so the last one is we have to make this value as a 1, right? How can we do that? Just divide row 1 by what? 3, right? Yeah, finally we get the row 1, row 2, row 3 like this with the 3 pivot position, right? And there is the zeros below and above of the pivot positions like this. So we could say this is the reduced echelon form of the original matrix. Okay, so this is the, so we got the reduced echelon form of the original matrix. What is the reduced echelon form is important? We can easily find the solution of this reduced echelon form, and then that solution will be the solutions of the original matrix. Okay, so that's what we have done so far. To summarize, in the low reduction algorithm, there was the 5 steps, right? So the step 1 through the step 4 is called the fourth page. In the fourth page, we want to make the original matrix as a echelon form. Okay. Echelon form. And then in the step 5, what do we want to do? We want to make the unique reduced echelon form. We know the reduced echelon form is unique for arbitrary matrix, right? So this is called the fourth page of the low reduction algorithm. Okay. To summarize, okay, we have a matrix A. We want to find the solution of this matrix A. What do we want to do? We want to find the reduced echelon form of this original matrix. Let's say REF of matrix A, right? So how can we do that? Using some kinds of low operations. We will find the echelon form of the A, and from the echelon form of the A, we can derive the reduced echelon form A like this. So in the low reduction algorithm, this procedure at the steps 1 through the 4. These steps 1 at the 5. So this whole procedure is called what? Low reduction algorithm. Yeah, that's it. We have a very powerful algorithm to solve any kind of the linear system using some row operation and use the very powerful form of the matrix like the echelon form and the reduced echelon form. Okay, so this is the row reduction algorithm. Actually, row reduction algorithm is the most important concept from lecture 1 through the lecture 2 or other remaining lectures in this course. Okay, so this is the row reduction algorithm. Then, okay, using this row reduction algorithm, we found the explicit description of the solution set of the linear system, right? What does that mean? Okay, let's say we have some arbitrary matrix, then we apply the row reduction algorithm, let's say RLA. Okay, then we found this reduced echelon form, right? This reduced echelon form, okay, because we have a two pivot position here and the above and below part is 0 like this. So this is the reduced echelon form. In this case, what is the solution of this reduced echelon form? What is the solution of this reduced echelon form? To verify this, let's go back to the equation form of this linear system. So this linear system can be represented in an equation form like this and this, right? So in this case, what is the x1? What is x2? What is x3? What is that? What is that? Which values are satisfying these equations? Which values? Okay, let's transform this matrix like this. x1 is equal to 1 plus 5x3, x2 is equal to 4 minus x3, x3 is equal to x3. Nice. What does that mean? If we just say that x3 is equal to 1, x1 should be 6, x2 should be 3, something like this. And if x3 is equal to 2, x1 should be 11, x2 should be, what is that? 2, something like that. So it means that as you varying the variable x3, we can determine so many solutions of the x1 and x2, right? So in this case, we call the variable x1 and x2 as a basic variable, and x3 on the other variable x3 is called the free variable. Okay. So what does that mean? So this free variable can be any numbers, and this basic variable are determined by this free variable. Okay. So this is the solutions of the linear equation. So whenever a system is consistent, do you remember what is consistent, right? In the last lecture. Then the solution set can be described explicitly by solving the reduced system of equation for the basic variable in terms of the free variable. So this operation is possible because the reduced echelon form places each basic variable in one and only one equation. So this is the concept of the basic variable and free variable. So this is the end of today's lecture. We will discuss further about this concept.